Okay, let's look at the last for this module, methods of eliminating the effects of ionic atmosphere on the conductivity of strong electrolytes. Remember, we've looked at the effects, both electrophoretic effect, asymmetric effects, and so on. So we want to look at the methods we can use to eliminate this. Application of higher frequency, application of very high potentials, and then we'll look at the findings from these theories and we'll conclude. Ionic atmosphere is a concept employed by Debye-Hurkut theory which explains the electrolytic conductivity behavior of solutions. That's what we have said before. It can be generally defined as area at which charged entity is capable of attracting opposite charge. So we have said all this: thickness of ion atmosphere, electrified interfaces, the general values, and so on. Now, this is a picture illustrating electrophoresis and the electrophoresis retardation. What we were saying, the ion atmosphere, look at the ion, is moving this way. Look at electrostatic force dragging it this way. Look at frictional force dragging it backwards. And look at this, is no longer symmetrical. If the ion were to be stationary, then you have something that is a complete cycle. But in this case now, there is a lag. The head is pushed this way towards the electric field. And then there is a electrostatic frictional force dragging it back. That is electrophoretic forces. And then when it is for cations, we say it's cataphoresis. Then for anions, we'll call it anaphoresis. So now, application of higher frequency. So if the conductivity is measured at high frequency by applying alternating potentials, the central ion moves backward and forward very rapidly, as if it moves front and back very rapidly. The time for this oscillation is small compared with the time it takes for the ion atmosphere to relax. So that happens, the consequence is that the central ion will be stationary. Its ion atmosphere will remain symmetrical. So if it is moving front and back, front and back, front and back, then the average effect is that the ion atmosphere will be stationary. Therefore, as the frequency of the potential increases, the relaxation and electrophoretic effect becomes less important, leading to an increase in the molar conductivity. And we call this Debye-Falkenhagen effect. This effect of application of higher frequency, which now eliminates relaxation effect and electrophoretic effect. We call Debye-Falkenhagen effect. You can also apply very high potentials. At very high potential gradients, an ion will move rapidly such that no ionic atmosphere has time to build up. You see, when it moves so fast, no ionic atmosphere will have time to build up. And this observation is what we call Wien effects. It's called the Wien effect. At very high voltage, relaxation and electrophoretic effect will be zero, and the molar conductivity will increase. The Wien effect is the experimentally observed increase in ionic mobility or conductivity of electrolyte at very high gradient of electrical potential. Now I want to look at the finding from these theories. The main attractive force between an ion and a surrounding water molecule is ion-dipole attraction. So we're talking about a dipole-dipole interaction between the ion and the dipole. The smaller the ion, the greater the binding energy between the ion and the water molecules. Lithium is particularly strongly bound to water, that it drags the water molecules during electrolysis, and therefore has lower mobility than sodium and potassium. Now, H.S. Frank described an ion in solution as having three distinct zones. In the immediate vicinity of the ion, there is a shell. We are going to look at, see a diagram. In the immediate vicinity, water molecules can be described as constituting the inner hydration sphere. Now, surrounding this inner hydration sphere, we have the second region called the structure breaking region. Here, the water molecules are oriented more randomly. In ordinary water, where there is considerable ordering due to hydrogen bonding, the occurrence of this structure breaking region results from two competing orienting influences on each water molecule, which approximately balance each other. One is the normal structural effect of neighboring water molecules. The other is the orienting influence upon the dipole. So one is the normal structure effect, the other is the dipole, that is the ion. Now the third region around the ion comprises the water molecules sufficiently far from the ion that its effect is not felt. This is a diagram. Look at the ion. Look at the other structure of water molecules bound tightly to the ion. We have the disorder, that is structure making forces oppose each other. Then we have the outer zone where ordinary water molecule, the effect is not felt here. We've come to the conclusion. Thank you very much, and I hope you enjoyed the class. See you in the next class.